So, good afternoon, everyone. It is very nice to see so many of you here again. My name is Yannis Saitis, and on behalf of Professor Avelpido, I would like to welcome you to our today's second trace workshop titled Reading the Past, Reconstructing Unseen Landscapes to Predict the Future. Last week's workshop, the Trace Decoding Landscape Change in an Era of Climate Uncertainty, was very successful thanks to your active and enthusiastic participation. So, today's workshop focuses on the coastal environment, emphasizing the methodologies used to study its past characteristics and its future evolution. Without further ado, let us proceed with our first presenter from the University of Bucharest, Professor Alfred Verspeneau Stroy. So, Alfred is professor of physical geography at the University of Bucharest, Faculty of Geography, and the head of the George Marine and Fluvial Research Station and of the Georadar Research Center for Geomorphology, Geoarchaeology, and Paleoenvironments. His research is focused on coastal processes, geomorphology, paleoenvironment, reconstruction, geoarchaeology, climate change, and periglacial process. So, good afternoon, Alfred. Um, Let me give you. Uh,
I already did.
you did it? Oh, perfect. Thank you very much, Elena.
Okay. Thank you, Yanis. Hello to everybody. So you already introduced me. We can start directly with the coastal lagoons. So I prepared a short presentation just to let time for questions and discussions publicly here. I will have a short introduction concerning the coastal lagoons globally, and then we'll have a presentation of the preliminary results that we got together in our cooperation Athens, Bucharest, concerning the Yarova Lagoon. So I will share my screen.
So we're meeting at 7, right? Up.
Okay.
Okay.
So do you see my screen now with the PowerPoint presentation?
We see
We can
your.
see also your notes.
Okay, so it's not what is. I will try again. Okay, maybe now it's better. Now it's okay. I think it's good now. Thank you, Yanis. So a few things generally about coastal lagoons, and we may start with their morphology and formation. They are very popular in different low-lying coasts because typically develop on low-lying coast, on gently sloping coastal plains, in micro and mesotidal environments. And they occupy almost 13% of the total coastlines in the world. And they normally develop in that coastal settings where coastal sediments are rich, are in excess, and most of them formed during the sea level stabilization, not exactly on the current position, but in the period that the sea level was just a couple of meters below, usually with 3, 4, 5 meters below, which means around 6,000 years ago. So if you are looking at the age of the coastal barrier initiation, which block these lagoons, we'll see that they form usually around 6,000 years, sometimes later, like 5 to 4,000 years, or in the proximity of the big river deltas in the world. We also have plenty of sediments on the upper continental shelf, and the datings should be older. Here, the coastal barriers close the lagoons close by 8 to 7,000 years ago. So this is about their age. And otherwise, the mechanism of closing the lagoon with a coastal barrier needs all the time plenty of sediments in the upper shelf on the shore face, which will be pushed up by the transgression, by the waves and storms during later stage of the Holocene marine transgression. Okay, so having this in mind, we may speak geomorphologically about a barrier lagoon system all the time because normally we call it coastal lagoon exactly this water body here behind the coastline, but it's also very important to learn more about the coastal barrier, which is closing and is evolving all the time under the pressure of the winds, waves, and currents. So the next step is to understand that every barrier lagoon system consists of three main elements. It's the lagoon by itself, behind. Then is the coastal barrier, which is composed all the time by sediments, usually sands, but otherwise are gravels or shingles, sometimes even reef, coastal reef, by corals. And the third element, which is usually present, are the inlets, that breakings, which allow for water to communicate in between lagoon and the sea. That's why in most cases, especially in the mesotidal conditions, typically the inlets develop also an tidal delta with these two compartments, in the flat tide delta and the ebb tide delta. But I will not insist today on these elements. Now, coming back to these three components, it's important to have an idea about the sediments which are colonizing them. So we have already spoken about the coastal barrier because it's composed by sands and shingles and the reefs. Behind the lagoon, it's finer, so we have muds, clays, and silts, usually organic rich, but the content in organic matter also is dependent on the climate. So if we have tropical lagoons, they will be very organic with frequency more than 40–50% of organic material into the sediments. If we are in a temperate region, should be less, like 10, 12, 20% of the organic matter present in the sediments. Otherwise, the inlets is composing usually with the same sediments like the barrier, so it's mostly sandy. And we might also speak about the connectivity of the lagoons with the sea. Here, it's a simple typology made by Kirfe, which just concerns the degree of connectivity. So the less connected are the chopped lagoons, which usually have just one small inlet. Sometimes even this inlet should be blocked by the longshore currents. Then is the restricted one, which is normally medium connected, and leaky lagoons, which are where the coastal barriers are presenting several large inlets, and the water from the lagoon is also well ventilated, well connected by the coastal currents in this case. Otherwise, in time, a lagoon evolves and becomes shallower. This is the classic evolution, but it's important to understand that the first stage, which is also the youthful stage, the first stage, normally it's just an open bay, an open marine embayment. And in other cases, it's a flooded river valley, which usually in geomorphology, we call it a Ria Valley. So a former river valley, which during the Holocene transgression becomes flooded, and then in the later stage, a coastal barrier is formed by the longshore currents and blocked this Ria Valley, transforming into a proper lagoon. And the late stage, the mature stage, it's that stage when the water lagoon becomes shallower and shallower, capturing sediments from two sources. The main source usually is the river, the catchment by itself, but also the storms are also contributing to the lagoon infilling by overwash processes, using the inlets especially, but sometimes even overwash overpassing the coastal barrier. Okay, and the last general discussion slide, it's about the subtype of the barrier that are closing the lagoons. So we have classic barrier islands. They are common in the deltaic systems, which are providing plenty of sediments, and the river mouth usually develops and feed barrier islands, which in time can become barrier spits due to the regression. But otherwise, we also have this kind of classic blocked valley, like in this case, it's Dnieper Valley. Here, you could see that in the northwest part of the Black Sea, different river systems were transformed in the lagoons. That's why it's a Slavic word for this lagoon type, call it liman. But in fact, liman is also a lagoon type. So it's when a valley, a ria valley, is transforming, is blocked. So we call it liman for this system. Okay, now we move with the discussion in the Peloponnese, just to have time to present also our results. For all of you, I think it's important to know that this lagoon, it's in the southwest part of the Peloponnese, the wettest region of the Peloponnese, so was all the time attractive for the population from prehistory till present, due to the excellent climate for agriculture also. And here we focused on the Yalova Lagoon, which is neighbored in the south by the Bay of Navarino, also and divided by a coastal barrier, and another coastal barrier, Voidochilia, which divide the Bay of Voidochilia by the Yalova Lagoon. And we'll try to show our preliminary results concerning the system, because I mentioned in the title, we have this Voidochilia Yalova coastal lagoon system. And this is a photograph overview of the region with a nice Omega Bay, Voidochilia Omega Bay here, and Voidochilia coastal barrier and Yalova Lagoon. Here it's the wall of the Navarino Castle, a Genovese one, in the southern extremity, beautiful. Here we have also a Mycenaean tomb, so it's and other Mycenaean tombs were already on the coastal plain or underwater, so it's very rich in archaeological remains. And I will come back to this figure just to say a few words about this Omega Bay. So look at the extremely perfect shape of the Omega Bay. This is a sign of long-term diffraction of the waves coming through this inlet and then dissipating the energy. And interesting, the size, very wide barrier in comparison with the bay. So just at a first look, we will know that it's an old system here, because you need a lot of time to capture the sands and create a wide barrier in this system. And this logics follows the wave height, which normally dissipates a lot and usually is relatively low. So if in this part we have a medium wave energy close by the shoreline, in every Omega Bay we have a low energy, low, because it's a protected environment. But otherwise, just see at the width of the barrier, which in this part is close by 400 meters, so very, very wide. It's a rich sedimentary archive composed by sands usually. Okay, and now I will present our coring strategy, which followed two purposes. One purpose was to use the Yalova sediments for reconstructing the paleo-tsunami in the area. And the other objectives was to find more about this coastal system evolution. For the first one, we need an crusher transect. It was important to have boreholes on the barrier, more specifically in the backward part of the barrier, then further landward and on a extremely landward position also, because we suppose that a tsunami should let imprints at big distances, which in this case are almost 2 kilometers far away by the shoreline. So that's why we have this kind of transect using 4 boreholes that we captured in 2 field campaigns in 2024 and 25, every time in October. And looking at the stratigraphy of these 4 boreholes, we notice that in the basal part, all of them have medium sands. Medium means relatively coarse, or even some coarser deposits contain a mixture of sands and shingles with this orange color here that we use. So the wider band we use, the coarser which should be that horizon. So the presence of the core sediments, usually at depths larger than 6-7 meters, it's a clear indication that we intercepted the former open bay phase, because you remember the first stage is just an open bay for every lagoon, even for Yalova. And stratigraphy normally is relatively similar, depends on the position. Maybe you notice that for Vidica 2 core, it's relatively coarser, but just have in mind the position. The position here was in front of a former river mouth position. I will come back at another slide just to see the Xirolagados River, which has this dramatic right turn here, but it's anthropically induced in the modernity, so usually it came close by our position. Vidicatu is positioned here. So knowing this, it's not a surprise to see that the coarse sediments appear relatively fast here on the Vidicatu, respectively of the depths of 5 meters. So here we intercepted the position of the river mouth in the past. And we also know the age, so it was somewhere before 4,000 years ago, this position. And after that, the water level continued to increase, and this imposed for the river mouth to be pushed back and to let this position to remain in the full lagoon. So for a while, the lagoon was even larger due to the sea level rise and the lagoon water level rise also. And this core transformed from a river mouth to a proper mid-lagoon position. Otherwise, even here behind at Vidica 4, you may notice the dominance of the fine sediments for almost 7 meters. So 7 meters of lagoon sediments dominated by clays. And this is classic, it's usual, it covered almost 6,000 years. So we have an idea that these coastal barriers formed somewhere between 7 and 6,000 years. We still are waiting for some ages. Here in the basal part, we have different OSL sampled, which are still in measurement in different labs to define as good as possible the transition from the open bay to the lagoon. And now I will present this data which recommends some depths on these boreholes to be paleo-tsunami. For this discussion, we used geochemistry and microfauna, but also the classic sedimentology. And you may notice these 2 blue intervals here marked, in which the mean grain size is rising, the sorting becomes poorer, and in magenta, the content in inorganic carbonates becomes high. Normally, these are clear indication of an allogenous input into the system. But this kind of evidences are not, let's say, enough to prove the presence of a paleotsunami layer. But anyway, it's an indication of clear indication that something happened from outside of the lagoon, bringing different nature of sediments. The other argument that we bring into discussion is the geochemistry. So we may use also zirconium rubidium ratio, which is here in blue, which normally increase proportionally with the granulometry, but much more important should be the ratio of the calcium titan or strontium titan, and also chlorine and bromur titan ratio, which becomes higher during the marine incursion, during the presence of some events which brings more saline waters, of course, with sediments. And maybe the most powerful instrument to look for the paleotsunami remains the microfauna, especially that kind of foraminifera, which are habitating at deeper depths, and also the presence of the marine species from Ostracoda intervals. And very nice. We captured that the transition from the marine to the brackish environment, it happened around 4 meters 80 centimeters, so here. So this is a very clear transition, which is not related by any tsunami or storms. It's just about the salinity into the lagoon, close by 5 meters. But after that, unexpectedly, around 3.5 meters depths, we noticed the presence of Ammonia beccari, in the same times with the Chitaromorpha fuscata, and the Loxoconcha species, which are pure marine species, and in the same time the Charophyta algae, which are indication of freshwater species, decreasing very much. So this is not a coincidence. This is a clear indication that here we had a period and an interval with very saline waters that appeared. How long it happened, we don't know for the moment, because it depends on the nature of the events. A tsunami may bring a few centimeters or may bring a few decimeters of sediment. So this may happen rapidly, like in a day, or this is what we are looking now to date as best as possible, as good as possible, this interval. So the same happened in this interval. I will not insist, are exactly the same phenomenon, which are describing a situation with an marine fauna, microfauna coming from outside the lagoon and most probably related by tsunami. So until this moment, concerning the paleotsunami issue, we had two events which are in progress in terms of dating with as good as possible H-depth models on several boreholes, which are also in progress. Further, I will have a few more slides concerning the coastal barrier evolution, especially the coastal dunes. Look once again at the surface area of the Omega Bay in comparison with the barrier. And already the barrier, it's larger than the bay. Maybe for you it's normal, but it's not normal. Look at the beach. The beach is narrow. The beach in Voidochilia all the time has just a few meters. So the berms there have 2, 3, 4, 5, 6 meters. Then it's a beach face and that's it. So it's a narrow beach just because the wave regime is low. It's a normal situation. And also the sediments are coarse, so it's a reflective. It's a, let's say, intermediate to reflective beach with narrow berms. So normally this is the sand brought by the waves and currents. Exactly that one here. All that happened here, besides, it's about aeolian processes. It was another theme, I will not insist, but just to know how interesting is also the polemics with other scientific teams, which, so it's a German team saying that these are normally washover fan. Maybe you know what are washover, so are that kind of units created during storms by the waves high enough to overpass the beach and to create. And sincerely, they look like washover fans. But if we are studying in the field, we'll see that everything is accommodating high dunes. We may call it better a dune field already, this part. And that's why we consider to be, in fact, just a problem of wind transport, of wind sand, Aeolian sand transport, and not beach, not washover fans. In fact, the strongest storms in the present, maybe Yanis know better, are just able to erode here, to erode the creating the existing dunes and not to create washover fans in this case. And we tried to make some analysis and computation using the wind data, just to see how was the potential Aeolian transport in that case. And we used some models. They are relatively old, but remain using in the present. Created the most popular. It's this belonging to Freiberger from 79, was applied in different also deserts of the world, like Kalahari and Gobi. And you are using wind speeds, all the cases which are above the critical wind transport, which is above around 6 meters per second. And finally, you'll derive a total drift potential expressed in vector units. And then you also may assess the resultant drift potential, which is just a value saying how strong is the drift into one direction. And the direction, we call it the resultant drift direction. Using this equation, you may find which is the direction that the grain sands finally will be transported. Of course, they are transported in each direction the wind is blowing, over 6 meters per second. But finally, it's like moving in a zigzag, but towards a direction. And this is the sand rows. We call it sand rows. It's Freiberger proposing these terms. As long it is a segment, as strong is the sand transport from this direction. So we may say that this sand rows from Voidokilia, it's an obtuse bimodal distribution with two main directions. The main is from the northwest and the secondary is from the east-southwest. But just look at the red arrow, which is representing the resultant drift direction, which is a clear southeast, and which is well aligned with the direction of the transport from here. Maybe even in the dunes it's a difference. If you are very careful, you see a small difference in between this parabolic transgressive lobe here and this one here. So it's a few degree direction. We just started the detailed study of this, and this will happen due to the topography, because these climbing dune are overlapping rocky platform. In fact, a former marine terrace. I don't know if it's from MIS 5E or, but anyway, it's a high obstacle which are disturbing the wind and are diffracting the wind, which will become a little more southeast directed in this part. So if there are some small differences in between the theoretical result in the right direction and this sand migration, should be also related by the presence of this obstacle. So these are the preliminary results that I wanted to share with you, and I would be happy to have also some feedbacks to discuss. And if I finished my talk.
Thank you, Alfred. It was very interesting first to have an idea about how the beach, let's say, ridges are formed, and then going to our study area. So first of all, you haven't stopped sharing your screen, so we're seeing an OSL result right now.
Okay. Yes, I will. Okay.
Okay, nice. So we have few minutes for conversation about what Professor Stroe has already presented. So, is anybody here who would like to raise a question or something?
Yannis, may I?
Of course, Miltiadis.
Thank you, thank you. I would like to ask if you investigated if the tectonics have affected the area and how this is represented into the boreholes. Do we have any tectonics in the area? I'm not familiar with the area. That's why I'm asking.
Okay.
So I didn't understand very well what exactly should affect the coring, or what was the term?
No, if we have an uplift or a subsidence in the area and how this affected the evolution of the soil.
Okay, now it's very clear. Thank you for the question. Oof, it's delicate. Normally, it is a slightly uplifting area here, but being very fractured by the fault systems, that fault, for instance, which is affecting like also in front of the cliffs and behind the chalk cliffs to the lagoon. The question it is if the lagoon by itself, if the Yalova is in the present uplifted or not. Sincerely, today I think we should have an answer when we are finishing the age depth models, because we'll compare finally the but at least two things. One, we'll see how how conform it is the same chronostrata in between different boreholes. If will be some, some differences, should be an indication of moving tier. But much more important will be to see the position of that chrono interval in comparison with the sea level reconstruction using different glacial isostatic models. So I think just using this kind of studies with a good chronostratigraphy, we will know more about the neotectonics in time, because otherwise, of course, you can find some direct measurements for 10 years or something, but not for the lagoon, for different, different points. But otherwise, you need this. So please ask me again in 1 year. Yes. Thank you.
Okay, thank you, Miltiadis, for this tricky question, let's say. Um, so, um, is anybody else who would like to raise a question here? Because the area of Yalova is a very unique area, affected from many sides, let's say, of winds and waves and currents and all these things. So it's a very interesting area for research. And also we learn also from this area, I mean, by the ongoing study.
Yeah.
Yanni, do you have also the development of beach rocks around the area?
No, well, there is some of them, few, on the northern part, but it's not very close to this area. I mean, it's around, Eliana, I think it's around 2 kilometers
Romanos?
on
Yeah,
the north.
but they're not extensive also. I mean, it's a
No,
small beach that has some beach rocks there, but they're not extensive in the sense of what you have in mind, probably.
in general, the west, the southwest part of Peloponnese is not characterized by beach rocks, to be honest. Yeah, it's highly active tectonic. That's why. Okay, then. Thank you very much, Alfred, for your presentation. I don't
Thank
see
you.
anybody else who wants to ask. Last chance? No? Okay. So, thank you very much.
Thank you.
Let's move on to our second presentation from Florin Tatui. Florin Tatui is Associate Professor at the Faculty of Geography at the University of Bucharest. He is affiliated to numerous international and professional entities, and right now he is the president of the Romanian Association of Geomorphologists. His main research focus is on coastal geomorphology, morpho and hydrodynamics at various temporal and spatial scales, surface and shoreline dynamics, sedimentary exchanges between the near shore and the beach dune system, coastal hazards and related risks, storm impact on low-lying sandy beaches, integrating coastal zone management, and many, many more stuff. So, Florin is going to talk about the deltas in risk and mainly on the Danube Delta. So, Florin, the floor is yours. Thank you very much for being here with us. I think we see your screen loading. But you're in mute, so we cannot hear you. I don't know if Florin can hear us. Until Florin respond, I would like to mention also that in the chat, Evangelos Spyrou has pasted, let's say, the call for you in order to, let's say, fill in your participation form. Okay, so please don't miss this chance. We're going to repeat it here and there during this workshop, but please do it as fast as you can. Florin, can you hear us? I think he's not.
It looks like he's disconnected because I think his
Yeah,
screen was stuck before.
yes. He's back.
Okay.
Okay, I'm very sorry. Hello, everybody.
Don't worry.
I'm at home and I have some problem with the internet connection. So hopefully, I would be able to to give this lecture. So thank you very much, Yanis. I'm sure that you did a very good presentation of me. So uh, okay, so I will share my screen.
Mhm.
Let's see if it works. And I apologize, but I will turn off my camera in order to save some.
It's better. That's what I was going to suggest.
Okay, so it's okay. Can you see?
We see your notes.
Let's see
The
again.
presenter view. Yes.
Okay, let's try again with the second screen. Share.
Now we see your background. And perfect.
It's okay. Yes. Now.
Yep.
And I will. Okay, perfect. And I will use the. You also see the laser pointer.
Perfect. Working too.
Okay, perfect. Thank you very much. Thank you very much. So, for today, I prepared, let's say, an extensive presentation. I hope that I will stick into the half an hour time about the deltas and the risks associated to deltas, with some examples from the Danube Delta. These examples are doing in the Coastal Research Group at the University of Bucharest. A short outline of today's lecture. So, even if I think all of you know many things about deltas, we'll speak about deltas as socio-ecological systems. We will emphasize some key threats related to deltas, and afterwards, in the second part of the lecture, we will go to the Danube Delta and present it uh, as a case study in terms of vulnerability analysis and some insights for the future, which can give us some be applied in other deltas also. So first of all, what is a river delta? And we have here a very nice sketch from a recent paper conducted by Edward Anthony and collaborators. Basically, deltas result from a river feeding sediment into a standing body of water at a rate that exceeds dispersal processes. Leading, of course, especially in large deltas, to the accumulation of a considerable sediment mass, both on land, as you can see here, this subaqueous delta, but also in the subaqueous zone with this subaqueous delta. And of course, delta existence has hinged on abundant sediment supply from river catchments, and we have these four steps in the development of a delta. There is a famous, let's say, delta delta type classification made by Galloway in 1978, and we classify deltas in three main types depending on the dominant driver for the development of a delta. And we have river dominated deltas, as you can see here, with this elongated bird food shape where the river energy is dominant, and we have a nice example in the Mississippi Delta. Tide dominated deltas where the tidal forces dominate, and you basically they have these elongated sand ridges, and Ganges Brahmaputra system is tide dominated delta, and wave dominated deltas where the wave energy shapes the shorelines, creating this smooth delta, and the nice example is the Nile Delta. In this recent paper, Professor Anthony emphasized three phases in the development of a delta, and they are nicely sketched in this diagram. So basically, the deltas started to form around 80,000 years ago when the sea level started to stabilize. So before, because the sea level was rising, the rivers couldn't compete with the rising sea level, so they couldn't form deltas. Once the mean sea level stabilized, the rivers and the sediments from the river started to form this deltas. And there is a first phase between around 8,000 years ago and 6.5 thousand years ago, when rivers formed this kind of bayhead deltas through aggradation. And in this phase we have the earliest human incursions, because we will see that humans were always related, or human occupation or always related to the presence of deltas. The second phase, starting around 6.5 thousand years ago to 2000 years ago, we have a period, this one P2, it's a period of aggradation, expansion, avulsions, um, and we have a significant growth in human occupation this time. So, and the third phase, from 2000 years ago to the present day, we have a period of continuous progradation with large-scale human occupation, which in turn directly modified the deltas, increasing this distant human impact. And in today's lecture, we will focus on this period, let's say the present period, with an increased human influence on many of the world's deltas. Here we have just some of the major deltas of the world from the same study, just to have an idea of the regional distribution of the deltas. The biggest deltas are in Asia. We have many important deltas, especially in terms of human occupation and also dynamics in Europe. We have some in Africa, also in South America and North America. If we have let's say if we want to see a global overview of the deltas, there are around 700 major deltas worldwide, covering around 500,000 square kilometers, and they are host of around 350 to 500 million people, which means 4 to 5% of the world's population. But and we have 10 of 34 mega cities of the world inside these deltas. But if we take into consideration, let's say, a distal limit of 100 kilometers from the shoreline, basically in these delta-related areas, we have around 40% of the world's population. So even if deltas cover only 1% of the land area and only 5% of the world's coast, they are really, really important in terms of human occupations. And we will see they are very, very fragile environments. And we have here a selection of major deltas around the world with the corresponding river and the area. And we will talk today especially about the Danube. Now, delta as socio-ecological systems. So besides being, let's say, host for this huge amount of population, there are a series of ecosystem services provided by deltas. For instance, they provide freshwater supply, they provide food, fish, rice, crops, also all kind of materials, and they also recharge the drinking water reservoirs. They are regulating floods. Also, they attenuate the impact of storm surges. They are areas, very important areas for carbon sequestrations and also for water purification. They also have important, let's say, cultural value in terms of cultural heritage and identity, tourism, scientific research, and also aesthetic value. And they support biodiversity, being biodiversity hotspots. Also, they are habitats for fish, for migratory birds, and also they host rare endemic species. Now we will go to the key threats for deltas all wide. And of course, we have two types of threats. On one side, we have the natural hazards, and on the other side, we have the human-induced stressors. And yeah, they are increasingly vulnerable, and this vulnerability has clearly been a product of the Anthropocene, with the last 60 years of intense human modifications of landscape and also climate. Human actions upstream deprive deltas of water and sediment. Also, human presence and exploitation in terms of groundwater, gas, and oil extraction contribute to subsidence, loss of wetlands, pollution, and accelerated erosion. And in terms of natural hazards, of course, sea level rise accelerates this land loss and submergence. So, in deltas, we have a mixture between stressors related to nature, to natural hazards, intertwined with many stressors related to human influence. And in terms of population, we have here a map of population living in large deltas in 2025, and we can see here large deltas, especially in Asia, that inhabit, let's say, tens of millions of inhabitants, and also related to the pressure of this population. We can see here a graph showing the continuous increase of total population in deltas from 1975, when we had, let's say, 150 million people, to over, let's say, 400 million people living in deltas nowadays. Of course, they put a lot of pressure on resources, on all the landscape. We have a map related to anthropogenic area in percent. So if it's going to yellow, means that 100% of that area is no longer natural, but influenced in any way but by human interventions. And we see again these Asian deltas that they barely have let's say small areas natural. Everything is human influence. And also in Europe, if we take for example Rhine Meuse Delta or Rhone Delta, they are highly influenced by humans. And in the bottom graphs we have some examples from Ganges, Brahmaputra, Rhine, Meuse, and Mekong. With yellow, we see agricultural land. With red, we see the built-up area, and with gray, we barely see some gray in these images, is the natural area. So people modified, especially let's say in the last century, in the last 50 years, heavily modified the deltas. And how this work? And we will take as example the Mekong. And in this diagram, we have the main drivers in italic and the consequences in bold. And for instance, we will talk today about the reduced discharge and sediment supply because of the construction of dams in the watershed. So this means that we have limited supply of sediments, both for the floodplain, so for the subaerial part of the delta, and also for the coast. So this means that the floodplain cannot cope with the sea level rise, and also that the coastline has no sufficient sediments in order to cope with with the erosion. Of course, we have all kind of land use changes in the floodplain. We have groundwater extraction, also sand mining, oil and gas extraction, and these are amplifying the land subsidence. So normally, naturally in deltas, we have compaction of sediments, which gives a natural land subsidence. But in many deltas, for instance, in Mississippi Delta, because of gas and oil extraction and also groundwater extraction, and in Asian deltas, mainly because of groundwater extraction for irrigation, so for agriculture, we have an increased land subsidence, and I will show you immediately some graphs about this. So we have increasing land subsidence, we have global sea level rise, so we will have an increase in the relative sea level rise, which will generate erosion, flooding, and also surface saline intrusion, which of course has an influence on the biodiversity of deltas. So we have all these types of connections you see between natural factors and human induced factors, which are increasing the vulnerability of deltas to climate change, especially. So in this threat landscape, we talked a lot about land subsidence, and there is a paper just published last month in Nature dealing with land subsidence and also sea level rise in global deltas. And you can see here with yellow and orange the subsidence rates in centimeters per year for some major deltas. And on the right hand side we can see the absolute sea level rise also in centimeters per year. And we can see that in many deltas the subsidence rates exceed the absolute sea level rise. So if we want to speak about the stress imposed by this to a delta, we have to combine these two stressors. So the subsidence rate plus the absolute sea level rise gives us the relative sea level rise that these deltas experience. And we have also these two graphs showing, for instance, the population that, for instance, here in this part, that have to face high subsidence rates and also high absolute sea level rise, Branta, Sierra, Chao Phraya, and the others. And on the bottom side, we see the population exposed to less than 1 meter, which leaves in between 0 and 1 meter above sea level. So this population will be heavily affected by subsidence plus absolute sea level rise in the future. And this is synthesized, let's say, from the same article in this graph. Here, the colors are expressing the population below the mean sea level, and the exposed area below mean sea level, and the circles the exposed population below mean sea level. And you see, for instance, in Europe there is a problem with Rhine, Rhone, Vistula, also in the Mediterranean, the Nile Delta, Mekong in the and Godavari deltas in Asia, Mississippi, North America, and so on, so forth. So most of the world's deltas are vulnerable to relative sea level rise in the present. Also, a background problem that I was talking about a few slides before is the diminishing fluvial sediment supply because of the construction of dams in the river watersheds. And for instance, nowadays the fluvial supply is 50%. So we have like 50% drop in the Anthropocene of this fluvial supply. Besides this, or related to this, there is a higher degree of fragmentation in most of the world's watersheds, and there is this paper of Greek Reuters from 2019, and with red we see that almost 70% of the global watersheds are affected by this degree of fragmentation. So we do not have a good connectivity in order for the water and sediments to arrive to deltas. And what is the direct impact of this? It is coastline erosion, and there is a and we see here with red the proportion of deltas with retreating shorelines, and we see lots of red. And in the bottom graph, we see the delta vulnerability in terms of coastline erosion. And with brown, we see that they have a degree of 4 degree of vulnerability. So this means that they are highly vulnerable to erosion. And you see many of the European deltas, also Asian deltas, are facing this. And to wrap up, before going to the Danube Delta, so the global mean sea level is rising nowadays with 3.6 millimeters per year, but the projected sea level rise will be somewhere between 30 centimeters to 1 meter by 2100. The problem is that because of the local subsidence in many deltas, the relative sea level rise is between 1 and 3 centimeters per year. So the deltas may sink faster than sea level rise, amplifying the flood risk. And in terms of sediment deficit, we have between 50 to 90% less sediment delivered to deltas. This is trapped in the upstream dams, and of course this means that the delta building slows or stops, and we will see a nice example from the Danube Delta, and we will have an accelerated erosion in terms of coastal coastline, let's say. Can you confirm that you are still hearing me?
Yes, yes.
Always.
Okay, thank you, thank you. So we are going to do this as a case study, and of course, the Danube Delta is interesting not only because we are working there, but because it is the Europe's second largest delta after the Volga, and of course the biggest delta of the European Union. And I have here I listed some interesting general things about the Danube Delta. Is an UNESCO Biosphere Reserve, Ramsar wetland, and World Heritage Site. So it has the highest status of conservation, let's say. It has three main branch. I will show you immediately, and it's a biodiversity hotspot with more than 1,800 plant species, more than species, lots of fish species, and also it is the world's largest compact reed bed. So many things to be preserved. And yeah, this is a map. Let's satellite image of the Danube Delta. Um, Here is the border with Ukraine, so we are sharing a small part of the delta with Ukraine, and this is the northern branch, which is called Kilia, and it forms this secondary delta, and this was formed in the last 300 years. The middle branch is called Sulina. It is the main navigable channel of the Danube Delta, and the southern branch is called Sfântu Gheorghe. It is a natural channel, and you can see here two images. The uppermost images are from the fluvial delta, so from this part, which formed between 8,000 years ago and 5.5 thousand years ago, and these are from the maritime or marine delta, this part, which formed in the last 5,500 years. Of course, it's very important to know what is the wave regime here. So we are in a medium wave energy with a significant wave height of almost 1 meter. The waves are coming mainly from northeast. So the direction of the longshore sediment transport is directly, most of the time, from north to south, reaching, let's say, for example, at the Sfântu Gheorghe mouth, 1 million cubic meters per year. In terms of sediments, we have sands up to 5 to 7 meters depth. Afterwards, the sediments are becoming finer and finer, going to silts and clays, as you can see in this map. So these were just some general, um, uh, let's say, information to set up the scene for the vulnerability analysis related to Danube Delta. And today I will focus only on the physical parameters. So I will not go into socioeconomic problems because there are plenty, but it will take, I don't know, a few hours more maybe to discuss about that. So in this vulnerability analysis, sea level rise, and you can see here some time-lapse images of a former accumulative area in that Kilia delta, and we can see that after these are images from the 1984, so Landsat images, but this erosion started 60s in the 60s. So we have all these problems, let's say, related to shoreline erosion, and it's very important to understand the causes and consequences of this erosion, because yeah, this ultimately influences the fate of the delta. And I took two slides from my colleague Florin Zăinescu, who, let's say, Sfântu Gheorghe river mouth, and river mouths are very important for the development of a delta, because sediments are going there and they are building different lobes. So he imagined what is happening to Sfântu Gheorghe river mouth as a battle between storms, and you can see here the waves. So we have waves and they are generating longshore currents, which are redistributing the sediments alongshore. And of course we have floods, and you can see here the river muddy. So this means that we have a high sediment discharge, suspended sediment discharge. So there is this battle happening all the time of storms and floods of river mouths. And for instance, for floods, which, let's say, we have 1 million Olympic swimming pools and 100,000 trucks of full sediment, we need like 1 million waves, which is the equivalent of a few megatons atomic bomb, in order to dissipate and to spread around all these sediments. So depending on the balance between floods, which means the river input, so the river power, and storms, which is the marine power, so the waves and currents, we can have, let's say, an equilibrium. If they are the same, we can have an progradation of the delta, the river mouths, if the river is more influent than the storms. Or what is happening today, if the river is weak, so is not delivering sufficient sediments, and the storms are strong, we will have an erosion of that area. So you have to imagine all this, let's say, this picture. And now we will go to some results that we have at our coastal research group at the University of Bucharest. And in terms of shoreline change, you can see here the spatial variability of shoreline change in meters per year in between two separated periods, let's say. A more natural period from the half of the 19th century to the half of the 20th century. So 1 century, let's say, when there was not so the dams were not so important. And we can see here for the Kilia lobe this explosion, let's say, with rates up to 70-80 meters per year progradation, so advancement into the sea. And of course, afterwards we have sectors eroding and accumulating. And after the 70s, with this reduction we will see in sediment supply, we see lots of red, which means erosion. And even this lobe, which was prograding in the past, nowadays it is eroding, as you have seen here. And what we also did, based on some bathymetrical data obtained from maps, we measured the rate of change in centimeters per year. If here we see this shoreline change in meters per year horizontally, we here in this graph we have to see this centimeters per year vertically, so aggradation, vertical accumulation. And you can see here in the second half of the 19th century, dominant accumulation. Afterwards, also accumulation up to 1935, and gradually to nowadays we can see this decrease in the aggradation processes. And the main driver for this is the very important decrease in the Danube sediment discharge. And you can see here a graph with the sediment discharge in million cubic meters per year from 1840 to the present. And you see this drop, first drop, let's say at the beginning of the 19th century, and the main drop was after the 1960s. And if you notice here the number of dams only in Romania, either on the Danube or on the Danube tributaries in Romania, we can see that after 1960s we had more than 200 dams constructed only in Romania. And in values, this means, for instance, that for Sfântu Gheorghe and for the others, nowadays we have 1/3 of the sediments which the Danube used to transport 100 years ago. And you can see also this data plotted on different time scales depending on the maps that we used in our studies. You'll say, what about the storminess? Of course, what happened with the storminess? And here are some proxies for the storms. We used this storm severity index and also the storminess index and wave power, and we can see that after a period of increasing storminess, let's say at the beginning of the 20th century, we had very high storms in the 60s and 70s, and afterwards, and even nowadays, we have a decrease in storminess and decrease in wave power. So we have a lower intensity and also a lower frequency of storms. So this should have, let's say, helped the delta recover. But because of the lack of sediments, we can see here in the 90s, 2000s, and afterwards that even for low storminess, due to the very low suspended sediment concentrations, we have lots of erosion. Even for this Kilia, you see it started with heavily developing, and afterwards it entered into this erosional phases. So nowadays, something like 65% of the Danube Delta coastline is eroding. What are the consequences? Because having, let's say, less and less sediment supply to the delta, we have some consequences in terms of coastal morphology and behavior. And we will take this example of the Kilia lobe. You see the shoreline was here around 70-50, and it developed a lot until, let's see, the 1960s, 1970s. And we can see this rapid development in this graph with this blue bars. In the 1856, the Kilia lobe was a river-dominated one. You see, it's very similar with the Mississippi, with this granulated shoreline, with many river mouths. This is a sign that the river was the dominant force that time. And in the present, you see a different situation. You see that the shoreline is linear, and we tried to emphasize this by shoreline length. So we have a higher shoreline length here because the shoreline is granulated, and the increasingly lower shoreline length because we have erosion and the sediments are redistributed along shore. So one consequence is this change in the behavior of a delta, and it's changed in the 60s from a river-dominated lobe to a wave-dominated lobe. Another consequence is on the southernmost river mouth at Sfântu Gheorghe. You see this image from 1857 and this satellite image from 2010. And here is a graph showing the central part of the river mouth. And we can see that, so from 1700 to, let's say, 1911, the river mouth prograded, so went into the sea because it accumulated a lot, and afterwards it started, you see, to move to the south. We call this a deflected mouth. Why is happening this? Because the longshore currents under the influence of waves are becoming stronger than the river input. We have seen that the waves are not stronger, are even weaker than, let's say, 70, 80 years ago, but the river is so weak that even these, let's say, low longshore currents can deflect this river mouth to the south. And of course, other problem which is super posed, let's say, on this sediment deficit is related to the engineering structures. And we can see here at Sulina mouth these jetties, so these parallel dikes into the sea. They have like 9 kilometers now, and they are we have, let's say, an interruption, a shortcoming of sediment transport along shore. These are highly influencing the sediment distribution along the Danube Delta coast. Uh, in the last years, we tried to use satellite images in order to get all these changes of shoreline, and we employed an automatic water extraction index derived from satellites, and we can obtain, using this index, automatically the shorelines. Each yellow line here represents a shoreline from 1990 to the present, and afterwards we used the digital shoreline analysis system, and we can plot this kind of graphs where each point is a shoreline position in a specific place, and you can see on the uppermost graphs some sectors eroding with rates of even 3 and more than 3 meters per year, and on the bottom graphs we can see areas prograding, but they are less and less. And this is an overview graph. So these are some mean values between 1990 and 2020, and you can see here, for instance, between Sulina and Sfântu Gheorghe area, that we have erosion rates up to 10 meters per year, also in this area up to 7-8 meters per year. And generally we can see lots of erosion, which is also depicted in this Hofmöller diagram, with red erosion and with gray accretion, accumulation. And we can see lots of red. And also we have, from 1990 to the present, we see an expansion of the red areas. And I told you that nowadays, let's say 65 or more than 65% of the coastline is eroding. In terms of subsidence, unfortunately, we do not have so much information. There are some studies in the past, in the 70s, 80s, and they say that the general subsidence in the Danube Delta is 1 to 1.5 millimeters per year, but we need a better estimation. Here, I just took a snapshot from the European Ground Motion Service, and they are using radar satellites in order to get this vertical motion. And we can see that even if we have only sparse areas covered with data, we have a subsidence rate around, let's say, 1 millimeter per year, but we need more data, especially in this southern part. There is a fault here, and this southern part is subsiding. We think it's subsiding, and we see from the course also that, yeah, we did it in the past, that we have this situation. In terms of sea level rise, Black Sea, let's say it's better than the world ocean. This is a graph from the Copernicus, and you can see that from 1999 to 2024, the trend is somewhere like 1.2 plus minus 0.8 millimeters per year. We have to compare this with 3.6 millimeters per year for the world ocean. So in terms of absolute sea level rise, let's say the situation is not so dramatic as in other deltas, but is it sufficient for delta survival? We will see. uh, I wanted to tackle also a little bit of the problems related to pollution and eutrophication, because the Danube gathers waters from 18 countries in Europe, also from different industrial effluents. We also have agricultural runoff with nitrogen, phosphorus, pesticides, and also we have pollution from navigation. And they are inputs for the Danube. Also, the suspended sediment binds contaminants, and this water and sediment arrives in the Danube Delta, and of course, pollution is a big problem, because this pollution, especially with nitrogen and phosphorus, produce algal blooms, also hypoxic zones. We have sometimes fish kill events, and in the Black Sea there is a problem with the loss of biodiversity, especially in the shelf area. And here we have two examples: an algal bloom from 15 July 2022. These green areas are with high concentration of chlorophyll A, and on the right hand side we have a natural colors image on A diagram, and the blue to green ratio from the satellite images, which can be used as an estimation, for instance, of the chlorophyll A concentration. So if we have low blue to green ratio values, this means higher concentration in chlorophyll A. So this means higher phytoplankton concentration and high probability of harmful algal blooms. So we are going to the end of this presentation. Some insights for the future. In terms of climate change, we have the projected impacts on the Danube Delta, and of course, depending on the climate scenarios, we can have a higher or very high increase in warming, let's say, in terms of air temperature, reduced summer precipitation. Of course, in the worst scenario, we can have 30 to 70% of the delta area permanently flooded or eroded, with salinity intrusion reaching to 20 plus kilometers inland, and of course, collapse of many ecosystems. So under high emission scenarios, the Danube Delta as we know it today may undergo irreversible transformation by 2100. So related to future dynamics of the Danube Delta coastline, even if the projected let's say storminess is lower, and you can see this in this graph, and also as you have seen, let's say we are in a better situation than other deltas in terms of absolute sea level rise. The fact that we have this continuous increase in sediment transport, we have this kind of engineering structures, and the worst thing, we do not have a sediment management from dams to coast, and not even a sediment management in the Danube Delta, and possibly other changes. And we have seen in the last years a change in the dominant wind direction. All these things could lead to extension and intensification of erosional processes, of course, with large areas of land loss in the Danube Delta. At the end, some responses and key takeaways. Of course, these are lessons from the Danube Delta. They are seen as transferable insights, and they are they can apply to other deltas worldwide. Deltas rarely face a single risk. And you have seen throughout this presentation that we have many risks related either to natural processes or to human-induced processes, and the climate, and they interact and amplify one another. So all these risk analysis must be integrated, and we are also speaking today by cascading events. We have to imply nature-based solutions in order to tackle these problems of erosion, sediment management, and so on and so forth. Also, we have to involve in this nature-based solution. We have to involve the local community and to take advantage of this local ecological knowledge in many of these implementation that we want to do in the future. Also, a delta is the product of its entire basin, so we have to think this as an integral system. In terms of governance, there are very complex areas, especially Danube Delta, because it's a transboundary area. So there are multi-level transboundary governance, which is essential, but is also challenging. And what is really important for us as scientists, that monitoring matters. So we need long-term ecological, hydrological, geomorphological data, and even if we have satellite data, these are irreplaceable. Even if we have models, we have to calibrate and we have to validate these models. And through these monitoring actions, we can help this evidence-based management of the deltas. And some conclusions: deltas are valuable, but also some of the most vulnerable landscapes on Earth. And managing all these risks associated to deltas requires integrated, multi-scale, and nature-informed approaches. So the technical solutions alone are insufficient. And the future of the world's deltas depends on this decision made today. And here I am in line with what Alasdair Skelton said last week, that some of this change stays in each of us. Thank you very much. If you have questions or
Thank you very
discuss,
much, Florin, for your
I think it
presentation.
was more than 30 minutes. Sorry about that.
It was, it was. So unfortunately, we don't have the time for a question, or if someone has very fast, short question, please uh, do so, or you may add in the chat the questions that are for Professor,
Yes, and by email
or
anytime.
email also, for
Yeah.
sure. At this point, I would like to remind about the participation list. Please don't forget to get in, fill your name and etc. Stuff. Um, it is essential. And also, I see here a question in the chat about the recordings and the material. I'm now pasting here in the chat this e-class link. In the e-class, you will find much more, let's say, material, educational material that our team, the Trace team, has developed. Also, there, after the end of this series of workshops, we are going to upload all the recordings for the from the workshop. So after the fourth one, you will see everything uploaded there. So thank you very much again, Florin. Please, I think you have to stop sharing your screen. Um,
He
so
has. Mm.
he, he does. He
Yes.
did. I still see his sharing screen. That's why. Okay.
Okay, just to add something regarding the e-class that Yanis added here. you need to create an account in order to be able to access the course. But it's very, very simple. It's free, and you just need to create the account. As soon as you create the account, you can go to the course. Sorry, Yanis, just to specify.
No, thank you, Eliana. Yes, it is a little bit, it is important, this kind of part. So, at this point, we're going to the final presentation from Eliana Karkani. Dr. Eliana Karkani is a member of the laboratory teaching staff at the Faculty of Geology and Geoenvironment of the National Capital University of Athens. Her research and interests are mainly focused on geomorphology, coastal geomorphology, coastal zone evolution at various temporal areas, natural hazard, paleogeography, and sea level changes. Elena, the floor is yours. Here you go.
Thank you. Let me share my screen. Okay. Can you see my screen?
Yes.
Yes,
Perfect. Okay, so I will try to not be very long. So good afternoon, everybody, also from me. We will move on now to Naxos Island. And we will talk a little bit about the different ways that tectonics and the climate can reshape a coast. So we will see various examples of paleogeographical evolution on the coastal zone of Naxos. So first of all, for those who are not familiar, Naxos Island is located just in the center of the Aegean Sea, and it's actually the largest island in Cyclades. You can see here in both maps that the Cyclades are basically in the center of the Aegean Sea, and they are considered to be a relatively calm seismic area, while the surrounding areas are characterized by high active seismicity. You can see that on the small map here. And most Cycladic islands are considered to be affected by gradual subsidence. But we will talk more about this during the presentation. So just to give you an idea, Naxos relief, as you can see on the slide, is quite mountainous. We have a central mountain range running from the north to the southern end. We have a maximum altitude of about 1,000 meters. And if you notice at the DEM here, you can see that the relief is more intense in the north and the eastern half of the island, where we have steeper slopes and deep valleys. But if we look at the western part, we can see that it is characterized by very mild relief, and we have the main plains of Naxos Island found here. So this is the area that we will focus on. So just to give you some more information, you can see on the left here, on the right, sorry, the dominant part of Naxos is comprised by marbles and schists, and we see that the western part is composed mainly by neogene and quaternary sediments, and we have this also extensive outcrop of granodiorite. And because we have this lithology on the island, and we have these different lithological formations with different resistance in erosion, we have the result of the present day morphology. And if we look at the coastal zone, you can see here two geomorphological maps of the island. We have very characteristic landforms like coastal lagoons, coastal dunes, tombolos, as well as beach rocks. And all these features are mainly located on the western coast of Naxos. So this is what we're going to talk about today. Before we talk about the Holocene, though, I'm going to share with you just a few slides to get an idea of how the area evolved during the Quaternary. So here we can have a look at the paleogeography of the wider area. 18,000 years ago, when the sea level was about 120 meters below the present one, and we can see that a large part of the Cycladic islands were joined together. And you can see that also Naxos and Paros was connected through land. And if we move a little bit in time, somewhere around 14,000 years ago, when the sea level was about 82 meters lower than today. We can see that slowly the islands are starting to get separated. And here we can see again the area 12,500 years ago, when the sea level was 43 meters lower than today. Actually, Paros and Naxos, these two islands, were separated about 8,000 years ago. So we can also understand that the coastal features that we see today on these islands are old and are of late Holocene age. And this is the area as it is today. So I will share with you some different researches that have been undertaken by our team during several years, investigating the paleogeography and the coastal changes on Naxos Island. And I would like first to start at the area known as the Laguna of Naxos. I have a short video here, but let's try to. So you've already heard a lot of things from Alfred from the first presentation about lagoons. So I will not take too much of your time here, but you can really understand that lagoons are very vulnerable environments to local changes, and they can be very powerful tools to understand the changes that have taken place in the coastal zone over the last few thousands of years. So coastal lagoons have the ability to record climatic changes, sea level changes, human interventions, and other environmental changes that are recorded in the sediments of these environments. And because we have this accumulation of sediments and organic material over time, if we study this type of material, we are able to unravel, let's say, the geomorphological evolution of an area. So what we actually did was some shallow sediment corings. You can see a compilation of the work basically on this slide. For the area of the Laguna, 3 cores were extracted with a maximum depth of about 5 meters each. And the work included to study the stratigraphy, the paleontology, the sedimentology, and the dating of findings using radiocarbon dating. And all of this information is synthesized in order to come up with the paleogeography of this area. The area is here. You can see with the red box for those who are unfamiliar with it. And here you can see some of the results from these scorings. It actually, as I mentioned, 3 corings took place, and you can see here the three stratigraphic columns and some results from the microfauna analysis. And based on the corings, we can see how the area evolved during the last 6,000 years. On this slide, on the left, you can see how the area used to look like 6,000 years ago. And on the right, you can see how the area is today. We can see that the area 6,000 years ago was a lagoon, while today it is a wetland. But in order to give you a better idea of how this area actually looked like, you can have a look also at the paleogeographic map on the top here. So the present day area, where it's actually also it's called the Airport Lagoon, was in the past the ancient harbor of Naxos. So we can see that the Laguna area used to look a little bit like this 6,000 years ago. And you can see on the bottom part some features that we can identify a little bit better that are present today. With the letter A that you see here, you can see the formation of a tombolo, and it's a more recent formation owed to coastal currents that transport and deposit basically the sand between the adjacent beach and the Mado Island that you see here. Then you see here in B, it's not very clear, but we will talk about them more later. We have some submerged beach rocks that are slightly lower than the sea level, and they reach down to a depth of about 2 meters, and they actually represent fossilized shorelines between the ages of 1500 to 3500 years before today. And what you see here with the letter gamma in Greek, but you see the present day lagoon. This area used to be a harbor, and it looks like it was an active lagoon from 6,140 years before present until very recently, and it probably served the ancient area of Iria, which is highlighted by the letter D here. And then we move on to a second case study, which is called Mikri Vigla. You can see again the area is here. A similar process took place also in the area of Mikri Vigla. With the 3 yellow arrows, you can see the location of the corings. And we can have a look also, and we can see that this area is also characterized by lowland morphology. There are some torrents that have a temporary flow. There is this coastal lagoon here, and there are also some submerged beach rocks in this part. And we have, of course, the coastal dunes in this area. So a similar process took place here. You can see on the lower part of the slide the 3 corings, the 3 sediment corings that took place in this site. And on the top part of the slide, you can see the paleogeographical reconstruction of this area. So on the left again, we see how the area used to look like 3,000 years ago, and on the right you can see how the area looks like today. So if we have a look on this part, we can see this line here that represents the beach rock barrier. And here, where we have these white arrows, is part of the beach rock that was subsiding periodically, allowing the water to enter inside the Gulf. And if we have a look also on the inland part of this area, we can see that the hydrographic network 3,000 years ago was probably discharged in the Vigla Bay area, but at the present day, the part of this network seems to have migrated to the southeast. So we can see that Vigla area was also a protected bay, like the Laguna Bay that I showed you before, by this beach rock bench, and the radiocarbon dating and the microfaunal analysis showed that at least during the Bronze Age, from around 3,300 BC, this was also probably a place where boats could anchor. So apart from corings, there are other elements on the coastal zone of Naxos that can also give us information about the paleogeographic evolution of several sites. I will not go into detail here. I would like to share with you one characteristic case study. You can have a look, however, in the map and see that in Naxos Island we have a lot of submerged beach rock slabs on this area, reaching down to a depth of about 6 to 6.5 meters below sea level. So we did multiple analysis on the beach rock slabs, which had to do with spatial mapping, cement examination, and we also performed luminescence dating on selected samples. And one of the case studies that we worked on is the area of Plaka. You can see an aerial photo here of this site, and in this area The deepest slab can be found at about 6.5 meters that I've mentioned to you before. And based on the OSL dating, we can have an idea. Again, this is the area of Plaka. We can have an idea of how the area used to look like. And based on the configuration, the submarine configuration of the beach rocks, we can have an idea of the coastal evolution. So this site is very representative and seems like it has very well recorded the morphological configuration of the coastline during the last approximately 4,500 years. If you notice the yellow lines on the satellite image, we can see that the submarine beach rocks can be followed almost parallel to the modern coastline for quite a few kilometers, more than 2 kilometers, and we can identify roughly 3 paleo shorelines, which you can see here. However, if we look to the north part of this satellite image, we can see that the morphology, the shoreline morphology recorded by the beach rock appears rather different. We can see that instead of being exactly parallel to the present day coastline, it appears to end up to a shallow outcrop of granodiorite. It is highlighted by this yellow circle, and this morphological configuration probably indicates that the morphology of this area used to be different in the past, with the presence of a paleotombolo, and maybe the existence of these two bays due to this the presence of this granodioritic outcrop. And I told you in the beginning that we're going to talk a little bit about tectonics. Another very characteristic landform that we find in the coastal zone of Naxos, but not only of Naxos, of nearby islands as well, is what we call tidal notches. Tidal notches are basically undercuttings that are cut in steep carbonate cliffs, usually near or at sea level. And based on previous research by Nikki Evelpido and some of her colleagues, they were able to identify 7 former paleoshore lines. You can have a look at the sketch here on the lower part to have an idea. And these former shorelines, represented by tidal notches, reach a maximum depth of about 2.8 meters. And the shallower shoreline was found at about 30 centimeters below the present day sea level. And by combining the morphology of the notches, the seismicity history of the area, and by also correlating findings with archaeological information, but also with the corings that I mentioned before, they were able to understand that there have been some rapid subsidence events that took place that were probably of seismic origin. And we can have a look again at this sketch. We can see that we have this shallower shoreline at about 30 to 40 centimeters below the present day sea level. And they were found not only in Naxos, but in other Cycladic islands. And this shallow shoreline is attributed to the global sea level rise during the last 2 centuries, but also at least partly by a very strong earthquake that took place at Amorgos Island in 1956. And if we look at the deeper shorelines reaching 2.8 meters, they are probably owed to repeated subsidence events and not to gradual subsidence. And this is also where tidal notches can help us. We can understand if the subsidence was fast or if it was slow. And by correlating these tidal notches with archaeological information and the corings, they were able to date the deeper notch at about 3,300 years before present, leading to a subsidence rate of about 0.8 to 0.9 millimeters per year. By combining all this, we can see also a summary plot of relative sea level changes for this area, which is combined by the cornings that I've mentioned before and by the beach rocks that we have studied in Naxos, but also in Paros Island. And by looking a little bit at the data, basically we produced the relative sea level index points based on all this data, and we compared our results with some modeled curves from two glacial isostatic adjustment models. And by doing so, we were able to calculate a tectonic subsidence rate for Naxos Island, because we had a mismatch between the models and our observations. And you can see here that we have calculated a subsidence rate of about 1 millimeter per year since 5,500 years before present. And this subsidence rate is clearly a combination of seismic events that are suggested by the tidal notches, but also probably due to the gradual long-term subsidence because of the area that we are in. But why does this matter? If we look at the sea level trends, Florine also mentioned different scenarios, different RCP scenarios. So if we look at this, the different sea level trends, we can see that in the future, we have a somewhat worrying picture. So we have more optimistic, moderate, and pessimistic scenarios for the expected sea level rise in the future. So depending on the scenario that we look at, we could even have, let's say, almost 80 centimeters of sea level rise by 2100. Or if we look at the rates, we may have between 4.3 to 8.4 rate of sea level rise again by 2100. So these scenarios actually suggest that they are characterized by very high vulnerability. And if we take this knowledge and apply it to the Naxos coastline, to the Naxos system, we can understand that the rising sea levels pose a significant risk for environments like these that we talked about, Naxos. And the tectonic subsidence that the area is undergoing adds basically to this rate of sea level rise, and it's exacerbating the risk of flooding or either erosion. So I would like to slowly close with very characteristic, some characteristic work that we did. I've mentioned also in the beginning that one characteristic of the western coasts of Naxos is the presence of very well-developed sand dunes in front of the coastal lagoons, as you can see in this picture. This picture is a very characteristic landscape that we see all over the western part of Naxos. Another characteristic, of course, is the underwater beach rocks that you see also here. So, in order to better understand how the area is today and what stressors exist in the area today, we did a study a couple of years back, and what I would like to share with you very briefly is some cross sections that we did in areas like here. This is the site of Agios Prokopios, where the yellow line basically shows where we did the transect, the cross-section, and here you can see the actual cross-section. So on this side is the sea, and on this side is the lagoon. And what we can actually note, and it's very characteristic, is that the well-developed dunes basically protect the landward part of this area from flooding. And this is very characteristic in all these areas. Here, for instance, you can see the site of Glyfada, and again, we can see here the same profile. We have the coastal area from this part, and we have the well-developed dunes, and we also have this lagoon. And most of these lagoons, I should also note that part of them is actually below the sea level. So these dunes play a very important part. And here you can also see some cross sections that we did to the coastal site of Plaka, which is located here, as you can see. We can see that it is a rather different setting in the sense that there are no coastal lagoons here, but we can see in most of the cross sections again that you can have a look here. We again have relatively well developed dunes protecting the landward part. The cross sections that you see here and the aerial photographs are from 2029, and I would like to show you some photos of the same sites, I think a couple of weeks ago. What you see here corresponds to a little bit to the north of this site here. And you can see that the area has suffered from some severe erosion and damages, and this is very, very recent. We had a storm that struck the area a few weeks ago, and it caused severe damage on the coastal area. We had a storm surge. We can see also that we have the development of a road here, and we have some buildings that have been built on the dunes, and they basically resulted in what we see here. So closing, I would like to, I'm closing with the slide to highlight that we have the climate change impacts and the climate crisis impacts, but we also have a combination of, let's say, human interventions. So we need to take all of this into account when we are talking about also the future of the coastal zone. Thank you for your attention.
Thank you very much, Eliana, for your presentation and traveling us to Naxos and the beautiful coastal zone of Naxos, of course. Let's say if we can have a couple of questions. We're just on time, so if there's somebody or some people who wants to give the questions, we may do that. Just raise your hands or open your microphone.
Can I ask something?
Yes, of course, Maria.
Hi to everyone.
Hello.
In the last photos in Naxos, in the point that it was erosional, it's a front of there's a front of a beach rock in front of this part of the beach.
Partly. There is part of this area has also some issues with the removal of the shallower part of the beach rocks because they wanted to allow access of the people to the sea. So it's a combination of problems that have happened in that area. So the road is constructed on the dune. You have also the removal of the beach rocks from the sea. So it's very easy to end up to something like we saw recently.
Okay, thank you.
Any other question? Okay, so if we don't have any further questions, we can finish our second workshop here. Please do not miss the third workshop next week, at the same time, not same place. You will get the new link. So the third one is on geotech in action, tools that reveal a changing Earth. So please do join. We would like to see you again. So until our next meeting, have a nice week, let's say. Thank you, all of you.
Good night.
Thank you.
Bye.
Bye.
Thank you.
Bye.
Bye-bye. Thank you.
Bye
Thank
bye.
you. Bye.
Bye.
My name is